Hello everyone. Today we are going to talk about Riemann integration. In the last two videos we motivated Riemann integration and also we talked about Riemann sum, which is a very important tool in this topic. Today we are going to use those knowledge to define Riemann integration of a function. And then we are going to cite a very powerful theorem by Cauchy which says that continuous functions are Riemann integrable. Then we are going to use this theorem with Riemann sum to integrate some functions, and finally I'm going to give at least one example of a function that is not Riemann integrable. So that's pretty much the plan for today. But before I get into the definition of Riemann integration, let me give you a quick overview of the things we have seen in the last two videos. Okay, so let's start with the area problem because that's the core of this whole story. Here is the area problem once again. And the setup was a non-negative function f. So let f be a function, a non-negative function. Defined on an interval a to b. Okay, and if I have a function like this, then I have a region that is bounded by the graph of f, the x-axis, and two vertical lines coming from those endpoints, x equals to a and x equals to b. The question is, what is the area of that region? Okay, so what is the area of the region bounded by the graph of f the x-axis and the vertical lines. X equals to a and x equals to b. Okay, so let me give you a picture of this kind of regions. So this is my x-axis, this is my y-axis, so this is my point a and this is my point b. Okay, and then I have, say, a graph of a function that looks like this. Let me make a little bit wavy. Okay, so this is my function, this is the graph of my function f. And then what region are we talking about? This graph bounded by this graph, the x-axis, and those two vertical lines. This line is x equals to a, this line is x equals to b. Okay. So it's pretty much this region in between. Okay, so what is the area, or how can we actually calculate that area? That was the question. And we have seen this thing in the last two videos. In the first one I actually showed you how Archimedes actually solved this problem for circles. So that was a really fantastic proof. And then we can actually extract the essence of that proof to deal with this kind of general region. So the ideas were this in short. So first we need to actually partition this interval. Okay, so number one is partition. So partition of an interval is it's kind of a set p x equal to x0, and then we have x1, x2, all the way up to xn, which is b. Okay, so we need a partition like this. So this guy is x sub 0, and then we have, say, x sub 1, and then we have x sub 2, okay, and then so this is x sub 3, x sub 4, x sub 5, and so on. Okay, and the last one is x sub n. So first we partition this thing, and the next thing is we need a representative points from each interval. So what is the goal actually? The goal is to fit rectangles on top of each of these subintervals. Okay, and for those subintervals we need some height, right, or length, and that length will be given by the value of the function at some point, and that point you can actually choose that point. It can be any point. Okay, so for this interval, let's say I choose this point as my a representative point, which we also call tags. Okay, so this is t1. Then here the rectangle will have height equals to f of t1. This height is the function f evaluated at t1. Okay, and then we make a rectangle like this. Okay, all right. So this height is f of t1. Now f of t1 times the length of this subinterval, which is x1 minus x0. That's the area of this rectangle. Okay. So what do we need actually in order to fit rectangles? We need points from each of these intervals. Okay, which we can call representative points or tags. So the next thing is that we need tags i.e. representative points. Points for each interval. Okay, and then there is a definition. It calls stacked partition, which you don't need to know if you don't like it, but it's pretty much this partition P. So we can actually write this partition as this. So we have different subintervals, right? So we'll call these subintervals x sub I minus 1 up to x sub I, right? Okay, and then I goes from 1 up to n. So if you plug in I equals to 1, you get x sub 0 to x sub 1, which is the very first subinterval. And then if you plug in I equals to 2, you get x sub 1 up to x sub 2, and so on and so on. Okay, and when I say tagged partition, then I list our representative points here. So t sub I. Okay, so t sub I is the ith representative point for the ith subinterval. Okay, so let's say this is x sub t sub 2 here, and then f of t2 is this guy. So we make a rectangle like this, and then here let's say this is my tag t3. So this rectangle will have this height. Okay, and then this is going to be t sub 4. Let's say we take x sub 3 as t sub 4. Then here we are going to, yeah, it should be like this, and then this rectangle will have this length, and then so this is t sub 5. Okay, then this is going to be the height, and then we get this rectangle, and so on and so on. Okay, so we fit rectangles, and then what do we get? We actually add areas of all these rectangles, right? So this is f of t sub I times delta xi, and when you add all of them, that's called the Riemann sum. Okay, so that was the third thing. And actually, the last video was all about Riemann sum. So if you don't know how to deal with Riemann sum, please go to the previous video on Riemann sum and do some practice. You need some practice. It's not hard at all. Okay, so number 3 is Riemann sum. Riemann sum of this partition. We denote this as S, F, colon, and then P dot. That means the tagged partition. Sorry, when I said tag, I put a dot. Okay, so this is going to be summation of all the areas of rectangles. So f of t sub I times delta xi, I goes from 1 up to n. Okay, so that's Riemann sum. You can also put an n here to mean that this partition divides your interval into n subintervals. Okay. So that's Riemann sum. But then just to give you, I mean, you can see this thing in the case of Archimedes, but also you can see it here. So this Riemann sum will have some errors, right? So here I have some extra area, but here I have some areas which this sum doesn't cover, right? Here we are getting some extra, here also we are getting some extra, right? Here we are getting something extra, but we are losing also something. So this all these Riemann sums will give you approximation. And the idea to get to the actual area is to make it very, very accurate. And the way to do this is this. Suppose you take a little bit smaller interval, okay? Okay, so now this is my partition. Okay, so now I have divided the same interval into more pieces. So what happened then, actually the corresponding lengths of the subintervals had shrink down. And then if I fit rectangles there, let's say we choose this point, okay, then we get this rectangle, and for this one, so we choose that one, then we get that rectangle, okay, and from there, let's say we choose this, so we get this one, and then from here, so this is my choice, so that one, and from here, let's say this is my choice, so that one, and for this interval, let's say this this is my choice, so I get that, and here, let's say this is the choice, so I get this, and so on and so on. So from here, what you have seen is you are actually minimizing the gaps, okay? You are refining your estimation. So that's the last thing. So that is called refinement. Okay? And this refinement, actually, what it means is you actually take the norm of your partition to go to 0. Okay, so what does norm mean? Norm is the maximum of the length of the subintervals, okay, delta x sub I, which is x sub I minus x sub I minus 1 from I equals to 1 up to n. So if you take the length, if you measure the lengths of each of those subintervals, you take the largest one, that's the norm. But if the largest one is getting to 0, that means those intervals are becoming very, very tiny, and so when you fit rectangles, it gives you very good estimate, which is actually the integration of the function. Okay, so far we have seen 1, 2, 3. All we need to talk about is point 4. Okay, so once we include that thing, then we actually get the definition of Riemann integration of a function. But now that actually involves some limiting process, and limit is not an easy thing. Okay, no matter what other people say, limit is very hard, and the precise way to define a limit requires a little bit of words. For every epsilon greater than 0, we need some delta greater than 0 to do blah blah blah. Okay, now we are going to actually capture all this essence into one statement, a limiting statement, and that statement will give us the definition of Riemann integration. And that's the next thing. Okay, so this is, I guess this is the last definition you need to learn in Calc 1. Yeah, this is a very important definition, by the way. This is very big. So definition, Riemann integration. Let f be a function defined on this interval a to b, then f is Riemann integrable on this interval a to b. So notice here we assume this interval to be closed and bounded. You can actually relax this thing, but for now let's just keep it like this. You cannot relax this thing every time. Okay, so then f is Riemann integrable on AB if there is a, or there exists a number L. Okay, this number L is going to be the integration. But the problem is it does not exist all the time. So we need to say very precisely when does it exist. Okay, if there is a number L such that. So now when I say such that, you see, then this kind of limiting behavior is coming. You need to define things in terms of epsilon and delta. Okay, and if you go back to the definition of precise definition of limit, you might have forgot all these things, but if you go back there, you will see the similarity of this statement with other statements, such that for all epsilon greater than 0, there is a delta greater than 0. Now this delta depends on epsilon. You change your epsilon, you have to you will get different delta. You have to get different delta. Okay, otherwise it's not possible. In all the cases, there is a delta greater than 0 such that if P dot, okay, so that's the tagged partition, right? So let me write it down. If P dot, so I'm writing here the partition and also our tags, the representative points, right? If Pi is any tagged partition of AB, okay. Now not all tagged partitions will be considered here. Notice the norm actually should be very small, right? Norm has to go to 0. So that thing should come up here, okay? Any tagged partition of AB with its norm to be less than that delta, okay? So if there is L such that for all epsilon greater than 0 there is a delta such that if this happens, then the Riemann sum corresponding to this stacked partition has the distance from the number L less than epsilon. That's the definition of Riemann integration of a function. I know this is mouthful, but if you remember the pictures we have drawn, all those analyses, you'll find this very convincing. It's very natural. Okay. So what we need here actually, this one is saying that our Riemann sums will approach a fixed number. Okay, and the better actually I want to make this thing, the better I can make by taking different partitions. So that's the essence of this thing. Anyway, we're going to use this definition to calculate some integration. But notice here there is something very important. It says that any tagged partition, okay? So this thing should be satisfied by all the tagged partition having norm less than delta. But how many tagged partitions are there? Infinitely many, right? It is really hard to check integrability. We can actually check differentiability of a function from limit of the difference quotient, right? But this is huge. It's not easy to actually figure out whether a function is integrable or not from this definition. Okay, But then we have a very important theorem, very useful theorem by Cauchy. So that will save our life. So this is theorem by Cauchy. Let f be if f is a continuous function sorry, let me write this way. Let f be a function on this interval a to b if f is continuous on ab but you can actually realize this thing at a finite number of points. Notice the graph I draw, I actually intentionally made it a jump discontinuity at a point, right? But that's okay. It does not actually change the area. So except possibly at finitely many points. So this is crucial, okay? If it is continuous on the whole interval, that's fine, but actually you can give a few points, finitely many points. That's also going to be fine, okay? If this happens, then f is Riemann integrable. Integrable on this interval a to b. Okay, we're not going to see the proof of this thing. It requires some calculation with partitions and refinement. But this will tell what? Most of the functions that you see in Calc 1 are going to be continuous, or they'll be continuous except few places, right? So you can always integrate them. Okay, so that integrability condition is kind of being taken care of by this thing. Okay, now I'm going to make 3 remarks here. So that L we talked about in the definition of integrability. Okay, if f is Riemann integrable on AB, then there is a number capital L, right, that satisfies this inequality for all epsilon. Then we denote L. Okay, so sorry, let me just write. Then we say L is the integration of f on AB, and we use a notation for that, and we write this thing, this symbol, integration of f from a to b, or we write this integration of f of x dx from a to b instead of L. Okay, so in calculus mostly you see like integrate this, integrate that, but there is a big question whether it is integrable or not, but that does not actually get much emphasized in this course. If you get to a higher course in calculus, then you will see this will be a very important point. Anyway, so once you know that it is integrable, then you can always talk about these kind of things. Okay, here f of x is called the integrand. A is called the lower limit, B is called the upper limit of the integration. Dx, a little bit, it will take some work to say what dx is. But right now dx does not have any meaning. Okay, so let's say this is remark. This x actually just means variable, so you can change this thing to say f of say s ds from a to b. Okay, so this is kind of a dummy variable in integration. Dx has a meaning, but that's out. That's hard to say in this course. Anyway, you can actually treat this as differential. Yeah, but it's not quite that. Anyway, so that's one thing, and the other important thing is this. Here in this theorem of Cauchy, it says that your function can be discontinuous at finitely many points, right? But actually you can extend this thing. You can actually extend this to okay, so this is the language. The set of discontinuity, okay, set of points where this function is discontinuous, as long as that has length 0, this is going to be integrable. So this is called Liebeck criteria of Riemann integration. So Liebeck is another mathematician. He came after Riemann. He actually improved this Riemann integration. Riemann integration is pretty good, but it has some limitations. And Liebeck actually solved those things. He strengthened this subject. So that is now called Liebeck integration. And that's why you always mention Riemann integration. Although at some point I will stop saying Riemann, because in this course we are not going to deal with Liebeck integration at all. In this course, integration will always mean Riemann integration. Okay? So the theorem of Cauchy will work, will hold as long as the set of points where f is discontinuous has length 0. Okay. Now this will, this can be explained in great detail, but I don't actually want to spend time on that. I just wanted to let you know that this is not the strongest version of this. Last thing, when we actually motivated the area problem, we always mentioned that our function is non-negative, right? But the way we have defined Riemann integration and also Riemann sum, we didn't actually say our function has to be non-negative, right? So Riemann integration can still work if our function is not non-negative only. It can be both positive and negative. Still we can find integration. So what does the integration mean? Okay, so this integration actually means the net area, okay, or the signed area of f on the interval a to b. So what does it mean, signed area or net area? It means that your function can be like this. Okay, so this is a, this is b, this is f, right? So here and there you get some positive area, right? But here when you form the Riemann sum f of t sub I, all of them will have negative value, right? Because they are below x-axis. Okay. So what it means is i.e. This guy, this is A1 minus A2, where A1 is the area of the region above x-axis, and A2 is the area of the region below x-axis. Okay, and then you take their difference. So that's what this integration means. If your function is always positive, then it definitely means just the area. Okay. Now, if you want to find area of the region bounded by this function and the x-axis, then what you need to do, you need to find this integration. That will be a negative sign, and then you need to take its absolute value, and then you add this with the area of those two pieces. That will give you the exact area. Okay. But if you integrate from a to b as a whole, that will actually subtract this area from those two. Okay, you lose some area because you are measuring, you are actually taking account the direction on which it is, whether it's on top or bottom, the x-axis. Okay. All right. So that's all about the remark. And now I'm going to use this theorem by Cauchy to integrate some functions. Okay. And I will do a very simple function, but that's complicated enough. If you understand that, then it's good enough for Calc 1, I think. Okay, so here's the question. Example, using the definition of integration, evaluate this guy. This integration, let's say x squared from 0 to 3. Okay. I know many of you know how to find antiderivative, and you are going to use what? Fundamental theorem of calculus, right? That's coming next. Fundamental theorem of calculus is a big thing. If we want to actually understand Riemann integration, we need to calculate some integration directly from the definition. Okay, so let's solve this problem. So what is the function here? F of x equals to x squared, and what is my interval? My interval is 0 to 3. Okay, is this function continuous on this interval? Yes, it is. X squared is a polynomial function, right? Okay, and that means this function is integrable. So this integration exists, right? Since f is continuous, let me write over there. Since f is continuous on 0 to 3, this integration exists. Okay. Now notice, what does the definition say? The definition say if it exists, then it should actually, you can calculate this using any partition, okay, whose norm eventually goes to 0. Okay. So we can actually take partitions which is the easiest to maneuver, and that is partitions all of whose subintervals have equal length. So delta x is constant. Okay, so we are going to do that. That will save our life. And what else can we do? We need to choose representative points. or tags, right? And it is always easier to actually choose the right endpoints, since here it does not say which points we need to actually pick for representative points, right? So we are going to pick the points which are easiest to us. Those are right endpoints, okay? So in other words, we are going to actually first figure out the right Riemann sum of this function on a partition that has all the subintervals of equal length. Okay, so let delta x. Okay, so let me just show you one more time. I showed you this yesterday in the last problem I did in Riemann sum. I actually showed how to calculate Riemann sum once we have all the subintervals of equal length. Okay, and once we choose the right endpoints. But I'm going to show you one more time. So this is x sub 0, which is your A, and then you get x sub 1, x sub 2, x sub 3, and so on, and the last one is x sub n, which is B. Okay, so that's your interval. You got this partition. Now notice all these subintervals have same length, right? Now how many intervals we have here? Subintervals n, right? So n times this common length equals to the length of this whole interval, which is b minus a. Okay, so let's say this guy is delta x, then this is also delta x, this is also delta x, unto the last, right? Then n times delta x equals to b minus a, so that means delta x equals to b minus a over n. That should be the length of each subinterval once you take all of them to have same length. Okay, so that's the background material. All right, so we are going to use this formula. Oh, actually one more thing. So if you know this is delta x, then what are x sub I? X sub I, notice the first one is 1 unit of delta x from x sub 0. The second one is 2 units of delta x from x sub 0, right? The third one is 3 units of delta x from x sub 0. So the ith one will be x sub I. This is, you start at x sub 0 and you go delta x units. How many times? I times. Okay. If it is 1, you go 1 time. If it is 2, you go 2 times. If it is 3, you go 3 times. If it is 0, you go 0 time. In that case, you just have x sub 0. That's it. Okay. All right. So we are going to use this and that here. So let delta x equals to b minus a over n. Now for this particular example, my b is 3, a is 0, right? So this is 3 minus 0 over n, which is 3 over n. Okay. And x sub I equals to what? This formula, x0 plus I times delta x. And now x sub 0 is a, which is 0, plus I times 3 over n. Okay, so this is 3I over n. Notice this I is not the unit of complex numbers I. That's a completely different thing. This I is just to keep track of the, those points. So this I represents for 1, 2, 3 up to n. Okay. All right. So this is x sub I. Let me just write that where I is between 1 up to n. Okay. Let me just show you in the interval what it is. So this is 0 to 3, right? So let's say this is 0. You plug in 0, you get what? 0 over n, which is 0, right? And then if you plug in 1, you get what? 3 over n. And then you plug in 2, you get what? 6 over n, right? And then you plug in 3, you get 9 over n. Okay? And finally you plug in n, you get 3n over n, which is just 3. Okay? So this is the partition of the interval we are talking about. Right? and all those subintervals have length 3 over n. That's what it is. Okay, so that's the partition, right? Let me graph the picture of this function. Say this is 1, 2, 3. Okay. This is 3, 6, 9. So at 1, this is 1. At 2, this is 4. And at 3, this is 9. Okay, so it looks like this. Okay, this is the function f of x equals to x squared. And we are concerned about area of this region. Finding integration of f from 0 to 3 means find the area of this region. Okay? Alright, and what we did, actually we figured out the partition of this thing. So this is 3 over n, and then this is 6 over n, and then this is 9 over n, and so on and so on. Okay, so these are the partitions, right? And now for each interval I need to fit a rectangle, right? And that's why I need to choose some representative points, and here I'm going to choose the right end points. So for this interval I'm going to choose that right end point, so my rectangle will have this height. Okay, and for the next one, so this is f of 6 over n, so my rectangle will have this height. Okay, and the third one will have this height. Okay. And similarly you can get the fourth one, and then the fifth one, and so on and so on, and finally we get this one. So we have partitioned that interval 0 to 3, we fit rectangles, right? And then what? We need to add the areas of those rectangles, which is Riemann sum, okay? And the Riemann sum we're going to take, to calculate that Riemann sum we're going to use right endpoints, okay? So the next thing is this, therefore, this chalk looks strange, okay, yeah. Therefore, R and F. Okay. So this is the right Riemann sum. So our tags are right endpoints. So these are going to be f of x sub I times delta x, and then I goes from 1 up to n. Okay. And what is x sub I? X sub I is 3I over n. And what is delta x? That is 3 over n. Now, what was my function actually? This function f of x is what? F of x equals to x squared, right? And so we are going to plug in those inputs in our function to actually calculate those outputs. So this is going to be, so if I plug in 3i over n, so this is going to be 3i over n squared times 3 over n. I goes from 1 up to n. Okay? Now 3i over n squared is just 9I squared over n squared and here I have 3 over n. Okay. Now notice this summation is happening on I. N is fixed here. N is the number of subintervals we started at the beginning. That's fixed. 9 times 3 27, that's also fixed. So we can just factor that out. So 27 over n cubed, and then here we are left with summation of I squared. And I goes from 1 up to n. So what does that thing mean actually? So this guy actually stands for this. If you plug in I equals to 1, you get 1 squared. If you plug in I equals to 2, you get 2 squared. If you plug in I equals to 3, you get 3 squared, and so on until the last one, which is n squared. Do you know what is the sum of this? Yeah, not many people know this thing, but I'm going to write the sum here. This is 27 over n cubed. So this, if you add all of them, there is a nice pattern for this. This is n times n plus 1 times 2n plus 1 over 6. Yeah. Okay, immediately you can cancel out 1n from top and bottom. You can cancel out 1 factor of 3 from top and bottom, right? And then what do you have? I'm going to keep that picture for a while. Okay, I'm going to finish the calculation here. So that means R and F is now, we'll cancel one of those n. So this is 9 over 2 and then 1 over n squared, n plus 1 times 2n plus 1. Okay. I want to do something here which I can do later, but okay, so here's the thing. So this is the Riemann sum when I have n subintervals. But in order to calculate the integration, I need to make my subintervals of really, really smaller length, right? In other words, I need to let n to grow up to infinity. So if n is going towards infinity, that means the length of each subinterval is how much? 3 over n. So 3 over n is going to 0, right? That means the norm of this partition is going to 0. That's what I need. So actually what I need here is to take limit of this guy as n approaches infinity. And that's going to be the integration of this function on this interval. Okay? In order to take this limit, something will be helpful to do. That is, since n goes to infinity, right? So this is a very common trick. We use this when we find horizontal asymptotes. X approaches infinity or negative infinity, right? So I will write one of these factors of n underneath of n plus 1 and the other underneath of 2n plus 1. So this will look like this, n plus 1 over n times 2n plus 1 over n. Okay, now this is 9 over 2. I can actually split this, so then this becomes 1 plus 1 over n, and this becomes 2 plus 1 over n. The reason why I did this is as n goes to infinity, infinity is not a number that we can plug in, right? If you say, oh yeah, the top goes to infinity, bottom goes to infinity, therefore this whole thing goes to infinity over infinity, which is 1, which is crazy. It's not true. Don't write that thing. Okay, that will not work, right? So you need to actually maneuver this thing a little bit. And the trick is this: you have, instead of n, you have 1 over n. And the good thing about 1 over n is, as n goes to infinity, 1 over n goes to 0. So this is a nice number now. That's also a nice number. Okay. Therefore, this integration Should I write here or there? I will write there on that one. Therefore, this integration of x squared dx, right? So that thing is actually the limit. Since this function is integrable by Cauchy's theorem, and then by definition we can actually take the right endpoints, so and then we can take all the subintervals of equal length. I mean, we can take this R and F, okay? And if we take limit of this thing as n approaches infinity, then that will also be equal to this integration, okay? Now that guy is 9 over 2 times 1 plus 1 over n times 2 plus 1 over n, okay? And 9 over 2 is a constant factor. You can distribute this limit. So the first one is 1 plus 0 and the second one is 2 plus 0. So this is 9 over 2 times 2, and that means this integration is 9, okay? So this area is 9. Okay. This is how we get it. All right. So if my function is continuous, then it is good. And we can find integration like this, right? But what is the point of talking about integrability? Are there functions which we cannot integrate? Yes. Okay, in this sense, yes. And I'm going to write a function like that, and I'm going to explain why it's not integrable. Okay, so I will start from here. Example, let f be the function given by this rule, f of x equals to, this is a very famous function, it's 1 if x is rational and it is 0 if x is irrational. Okay, the question is show that this function is not integrable on 0 to 1. This does not exist. Okay. Actually, there's nothing to do with this 0 and 1. I can change that interval. Still, it's not going to be integrable. I can also change those constants. That will also fail to be integrable. Okay, so how are you going to show that? Now the key here is this. What do you know from the definition? The definition says if it is integrable, then all partitions having the fact that the norm goes to 0, they will have the same limit. That's the essence of the definition, right? And for this case, we'll show that there are two partitions. Actually, there is one partition, but then we'll choose representative points in two ways. In the first case, we'll choose just the rational numbers. But then all the rational numbers will give us output 1, so that will give Riemann sum 1. And in the other choice, we'll take all our tags or our representative points to be irrational numbers. But then f of irrational numbers are 0. So all those Riemann sums will be 0, right? So you can get two different tagged partitions converging to two different numbers. That's enough to say that this function is not integrable. because if it were, then both of those partitions, tagged partitions, should converge to the same limit, but they will not. Okay, so that's how we are going to prove this. So solution. Okay, so our interval is 0 to 1. Okay, our partition will be just a regular partition having all the intervals of same length, just like this case. Okay, let delta x be b minus a over n. That means 1 minus 0 over n, that is 1 over n. Okay, and x sub I equals to x sub 0 plus I times delta x. Now x sub 0 is a, which is 0, plus I times delta x is 1 over n. So this guy is what? I over n. So that means, yeah, I actually have to draw a similar picture here. So this is, say, 0. Then the next one will be 1 over n, and the next one is 2 over n, and then 3 over n, and so on, until the last one, which is n over n, which is just 1. Okay, so that's the partition of this interval. Okay, and notice the intervals are like this. 1 over n to 2 over n, and then 2 over n to 3 over n, right? And 3 over n to 4 over n, like this. Okay? All right. For all I, so here I actually runs from 1 up to n. Okay, for all I, let's choose the points. Let's choose the points Ti, and yeah, we need a different name, so because we need two different selections of points. So Si, S for sum. So let's say Ui. Okay, and Ui, choose the points Ti and Ui from this interval, right? So what is the interval? X sub I minus 1 up to x sub I. Okay, which is, by the way, is I minus 1 over n to I over n. So these are the subintervals, right? So from each of those subintervals, we choose 2 points, Ti and Ui, such that Ti is rational, is a rational number, we need to remember this fact: output at every rational number is 1, output at every irrational number is 0. Oh God. Is a rational number, and Ui is an irrational number. Okay, and we define these two tagged partition. Okay, so for tagged partitions we need the subintervals. The subintervals are going to be the same. So this is I minus 1 over n up to I over n, and for the first one our tags or representative points will be T sub I. These are rational numbers. Okay, and I runs from 1 up to n. Let P dot be this and Q dot be this. Intervals will remain the same, only the tags are changing. Okay, so we get two tagged partitions. Now by definition, this function is integrable on 0 to 1 if both of these tagged partitions will give, if we form Riemann sums using both tagged partitions, they will actually eventually have the same limit. That's what the definition says. Okay. Now, S, let's put n there, f p dot. So Riemann sum of this function corresponding to this stacked partition p, this is going to be what? F of ti times delta x, summation of this thing as I runs from 1 up to n. Okay. Now here's the punchline. T sub I is a rational number, and the way this function works, whenever you plug in some rational number, it will give you 1, right? Output is 1. So this thing is what? This is just 1 times delta x. I runs from 1 up to n. But what is delta x? Delta x is just what? I over n, right? So this is 1 times I over n is just I over n, right? Actually, we can factor out 1 over n from here. So this is summation of I. Actually, oh, sorry, my bad. Delta x is 1 over n, sorry. Yeah. So you can, okay. This is, you just sum 1 over n times. So what is this thing actually? This thing means so first we take 1 over n for I equal to 1. Notice there is no I, so we just have to do the same thing. Okay. And how many of them? N terms here. So if you add all of them, right, so you get n over n, which is just 1. Okay. That means if you subdivide the interval 0 to 1 into n pieces, the Riemann sum is going to be 1. Notice the Riemann sum does not address n. So no matter how many intervals you have, I mean how big your n is, it's still going to be 1. In other words, i.e. or hence, the limit of this Riemann sum as n approaches infinity is just the limit of 1 as n approaches infinity, but 1 is a constant, so this limit is 1. Okay? And now we'll do the same thing with this stacked partition q dot. On the other hand, Sn f q dot, that means Riemann sum of this function f with respect to this stacked partition q. This is now going to be what? F of u sub I, right? Times delta x, I runs from 1 up to n. Now, u sub i's are irrational numbers, and f of irrational numbers are 0. So this is 0 times delta x, right? But 0 times anything is 0, so this is summation of 0. But if you add 0 as many times as you want, this is still going to be 0, right? So in that case, if you choose your tags or your representative points from each subinterval to be irrational numbers, then your Riemann sum is always going to be 0, no matter how many subintervals you pick. In other words, no matter what your n is. That means if n goes to infinity, this Riemann sum will have limit 0, right? Hence limit of this Riemann sum as n approaches infinity is limit of 0, and 0 is a constant, so this is 0, right? Now you have two different tag partitions which give you different limit. Two different Riemann sums corresponding to two different tag partitions which will give you different limits. Okay, since the limit of this is not equals to the limit of that, f is not integrable on 0 to 1, okay, i.e. this integration does not exist. Okay. So yeah, that's the end of this video lecture. That's all you need to know about Riemann integration at this stage. Okay. If you go higher and higher, there are many things you need to learn about Riemann integration. It's deep. Okay. So next time we actually want to talk about fundamental theorem of calculus, but maybe it will be a little bit helpful if we talk about antiderivative, but on the other hand we don't have much time. So I don't know what I'm going to do next, either antiderivative or fundamental theorem of calculus. Yeah, we'll see. Okay, so stay safe and see you next time.